Well, hello there. Welcome back to another round of Chemistry with Mrs. Jones. Today we're going to be talking about polarity, also known as the great tug of war in molecules and bonds. So as we've been talking about bonds in more depth here, we've been drawing a lot of Lewis dot structures and looking at some different shapes of molecules. We've been talking specifically about covalent bonds, bonds where those electrons are shared between the atoms. Sometimes, though, in these bonds, atoms don't share evenly. Most everything in chemistry is fair, but sometimes there's those bully atoms that like to steal electrons. And these create polar bonds. Polar bonds are bonds where electrons are not shared evenly. In these types of bonds, electrons get pulled closer to one atom than they do another. It's kind of like a tug of war between the electrons. So in atoms like this, carbon and carbon, obviously they're equal. They're the same atom. So their electrons would be shared evenly. But in atoms or in molecules like this, H and O, well, one is stronger. The oxygen in this case is actually stronger. So it takes these electrons and it pulls it closer to them. And then sometimes when we look overall at the molecule, the combination of polar bonds and where they're at can create polar molecules, but not always. So we can determine polar bonds by using electronegativity. And remember that electronegativity is the ability of an atom to attract electrons. And how these atoms attract these electrons kind of determines how much they pull on those electrons in the bonds. So we can look at these electronegativity values. I handed these out in class the other day. Remember that our trend is it increases as it goes across, and as it goes down, it decreases. Okay, so this graph kind of shows that. But we can look at these values to determine what's happening between those bonds. And we can define three different bonds in this way, three different sharing of the electrons. The first one is ionic. And this, again, not so much as sharing as stealing, because remember those ionic bonds, they're kind of like the thieves. They want electrons so badly that they take the electron away, and then they become charged, and the other atom is charged as well, is just attracted to it. It's the attraction between charges. These two bonds, non-polar covalent and polar covalent, they have the covalent in it. That means that they are sharing those electrons. In a non-polar covalent, atoms have very similar electronegativity values, so that they share their electrons equally. It's a fair sharing. In a polar covalent, however, atoms have very different electronegativities. One atom is going to want electrons way more than the other. So this creates a very polar situation, kind of like the poles at our planet. They're on one end or the other. This is the same thing that's going to happen in the bonds. Electrons are going to go to one end or the other. In order to determine if it's a polar bond, you just look at the electronegativity values using your chart. If the electronegativity value is between 0 and 0.3, it's a non-polar covalent. That means there's not much difference between the electronegativities. Both atoms want those electrons about the same, and so they share pretty equally. One's not stronger than the other. If the electronegativity difference is 0.4 to 1.9, it's a polar covalent bond. That means one of those atoms wants electrons a lot more than another. So it pulls those electrons a little bit closer to it. The great tug of war between those two atoms is won by the more electronegative atom. If the electronegativity difference is between 2 and 3.3, that means that there's a huge difference in electronegativity and the want for electrons. So that means one is just going to flat out steal one of those electrons. Makes those charges, and there's attraction between charges. So if we look at an example of HCl, the electronegativity of hydrogen, if we look at the chart, is 2.1. The electronegativity of chlorine is 3.0. The difference between these is 0.9. And if we look at this, 0.9 gives us a polar covalent bond. That means that the chlorine is going to steal some of those electrons and pull them a little bit closer. They're still sharing because we know that that it's covalent, so they're still sharing in between them, but one is pulling it just a little bit closer to it. Now when you pull an electron a little bit closer to you, you're pulling some negativity with it. That means you become a little bit negative. So when this hydrogen pulls this electron a little bit closer to it, it gains this partial negative charge. This goofy looking symbol here, you make it kind of like a S that connects, means partial. That means it's not a full charge, it's just a little bit of a charge. So it's a partial negative. We took that electron away from hydrogen. So if we take away some of its negativity, it becomes a little bit positive. So it has that goofy partial sign and a positive. In an ionic bond, they're stealing it all the way. So that would be a positive charge and a negative charge. But because we're only bringing it a little bit closer, we're not actually stealing it all the way, it's just these partials. This is going to give the molecules some new properties overall, and we'll kind of investigate these next week when we look at some of the labs. But you can see this a lot in water. If you've ever done the experiment where you drop pennies or paper clips into a cup of water and it gets really full and the water starts bubbling over the top, that's because of partial charges. These partial charges attract. A partial positive and a partial negative will come together and they'll stick. This makes for kind of sticky molecules because they like to stay together. And that's why water will bubble up and create surface tension. So the overall direction of the polarity in a bond or molecule is called the dipole moment. And we can show this by kind of what I've been drawing in here, just an arrow pointing towards the more electronegative atom. So overall, the polar bond is towards the chlorine, or the dipole moment is towards the chlorine. And this is going to start looking at molecular polarity. Okay, what we just talked about was bond polarity, where atom, and what's in between, what they're sharing those electrons, those are the bonds, and that's the polarity in those bonds. But if we look at all the bonds in a molecule, we can determine if the molecule is polar or not. So bonds can be polar, and molecules can be polar or nonpolar, depending on even if they have polar bonds within them. So there's three things that we're looking at for molecular polarity. Polar bonds, direction of all those dipole moments, or direction of where all those electrons are being pulled, and what the molecular shape is. So kind of what we worked on with that app the other day. So in this molecule, we can see carbon and oxygen. Well, oxygen is way more electronegative. And if we look at those values, it would give us a difference that would put us in the polar covalent region. So there would be an overall pull this way. So it has polar bonds, there's an overall direction of that moment, and the shape is linear, so that's not really going to help us any. It's not going to really change it. But in a molecule like this, all of these electrons are being pulled out, and if we were to look at this molecule in 3D space, it would kind of make one big tug-of-war that just cancels each other out. So nonpolar molecules are symmetrical and they cancel each other out. The overall tug-of-war from the center is a tie. So if we think about all of these bonds between boron and fluorine being polar, they're all being pulled out. And if we think of this as one big tug-of-war in the molecule from our center atom, this molecule wouldn't move. There wouldn't be an overall winner. And whenever there's no winner, it's a nonpolar molecule. Even though it has polar bonds, nonpolar molecule, because there's no overall pull of electrons in that molecule. If it's a polar molecule, dipole moments are asymmetrical. They don't cancel. So there'd be an overall winner in a tug-of-war with that molecule. So in water, everything's being pulled this way towards our oxygen. And so if we were to imagine a tug-of-war between these molecules, the molecule would go that way. Oxygen is having kind of 2 times the power of these hydrogens, and there would be an overall winner. So this molecule would be polar. Has polar bonds, there's an overall pull in that tug-of-war, so there would be a polar molecule. Polar molecules have polar bonds, The bond dipoles have an overall direction and a shape that allows there to be a tug-of-war winner. That's what to remember for molecular polarity. Bond polarity is between the electronegativity values. Molecular polarity needs these three things to be considered. So if you have any questions, just let me know. Otherwise, we will be talking about this a little bit more next week. I will see you then.